Welcome to AI Paper Podcasts. Today, we're diving into some really interesting research that's trying to make AI much better at finding security problems in software.
Yeah, it's a big challenge.
Exactly. We're looking at a paper called R2VUL, Learning to Reason About Software Vulnerabilities with Reinforcement Learning and Structured Reasoning Distillation.
Quite a title.
It is, but the core idea really is teaching smaller language models to think more like security experts when they look at code.
Okay.
So R2VUL uses reinforcement learning and this clever technique called structured reasoning distillation, basically showing the model examples of good security analysis versus flawed analysis.
Got it. So it learns to tell the difference.
Right. And the results are pretty impressive. These smaller AIs end up performing as well as, or sometimes even better than, bigger models and, existing security tools.
Across different programming languages too, I saw.
Yep. Multiple languages. Plus, they seem better at finding vulnerabilities the model hasn't explicitly seen before, and they handle data sets where safe code vastly outnumbers the risky code, which is, more realistic.
That's definitely important for practical use.
So, yeah, for anyone out there keeping track of AI and code security, this paper is definitely worth digging into.
Absolutely. The R2VUL team really zeroed in on a critical issue. LLMs are powerful, we know that, but for finding software vulnerabilities.
Well, their reasoning hasn't always been reliable. It's like just flagging code isn't enough. You need to know why it's a risk. And crucially, you need to differentiate a genuine problem from, a false alarm.
Exactly. And the paper really highlights why current LLM methods often fall short here. They mentioned chain of thought, for instance.
Right, VO2.
Yeah, it works well elsewhere, but for security vulnerabilities, the paper argues it often just lacks that deep security-specific understanding.
Well, it makes sense if you think about it. Code generation, for example, directly benefits from an LLM seeing tons of code during pre-training.
But spotting vulnerabilities requires this different skill telling secure code apart from insecure code. And that specific distinction isn't something that's really emphasized in, standard pre-training.
Which then causes issues with other methods too, right? Like just fine-tuning for classification.
Yeah, the CLS approach. You get a yes or no, vulnerable or not, but zero insight into the reasoning. It's a black box.
And even with standard instruction tuning, where you ask for an explanation.
The explanations can sound convincing, but actually be misleading from a security standpoint. Plausible, but wrong.
The paper had a good example of that, didn't it? With the Python logging vulnerability.
They did, yeah. Fortunate clouded it, I think. It was leaking sensitive data into logs CW532, if I remember.
Okay.
They tested a 1.5 billion parameter model using chain of thought on it, and it completely missed vulnerability.
Really?
Yeah, the reasoning it gave was super generic, didn't touch on the actual security flaw at all, just waved its hands, essentially.
Okay, so that definitely sets the stage. What's the core R2VUL idea that gets around these problems?
So the fundamental idea behind R2VUL is to explicitly teach the model to tell the difference between high-quality security reasoning and flawed reasoning.
High quality versus flawed. What does that mean exactly?
High quality means, first, getting the classification right, is it vulnerable or not? And second, providing a structured, logical explanation that backs it up. Flawed reasoning is getting it wrong, basically. Either the classification is wrong or the justification sounds okay, but is actually misleading.
I see. So how do they actually teach the model to make that distinction?
It's a two-stage process, which is pretty neat. Stage one is all about building a data set, a preference data set.
Okay.
They use a big, powerful teacher model, Quinn 2.5 Coder 32B Instruct, a 32 billion parameter one, and prompt it to generate both good and bad examples of reasoning.
Both. How do they get the bad examples?
Well, first they generate the good examples. They prompt it for structured reasoning about code snippets in C#, JavaScript, Java, Python, and C.
Structured reasoning. What does that look like? Is it like a template?
Sort of, yeah. It's inspired by how a developer or security analyst might break down the code. If it's vulnerable, the reasoning should pinpoint the bad code lines, explain the mechanism like how the flaw works, assess the potential impact, and link it to standard identifiers like CWEs or CVEs.
Okay. Very specific.
And for non-vulnerable code, the reasoning should discuss the code's security aspects and clearly justify why it's considered safe.
Gotcha. So how do they generate the flawed reasoning examples then?
That's the clever bit. They simply tell the teacher model the wrong answer. They take a vulnerable function, but prompt the model as if it were not vulnerable, or vice versa, and they ask it to generate a structured justification for that incorrect label.
Oh, I see. So the model learns to recognize reasoning that looks structured but leads to the wrong conclusion.
Precisely. It gets pairs of reasoning for the same code snippet. One high-quality, correct label, good explanation, and one flawed, incorrect label, misleading explanation. It learns the contrast.
And they showed an example of the good reasoning for that logging bug earlier?
They did, yeah. The 32B teacher model correctly identified the code, the mechanism, the impact, the CVE, much, much better than the generic chain of thought output.
Okay, so stage 1. Build this awesome data set of good-bad reasoning pairs. What's stage 2?
Stage 2 is where the learning happens for the smaller models. They use reinforcement learning from AI feedback, RLAIF.
Right.
They take that preference data set and use it to train smaller student models. They tried 0.5B, 1.5B, and 7B parameter versions. The training process essentially rewards the student model when it produces reasoning similar to the good examples from the data set, and penalizes it when it produces reasoning like the flawed examples.
And they use a specific RLAIF method, or RPO, odds ratio preference optimization.
That's right. ORPO is seen as a pretty efficient way to do this. Instead of needing a separate reward model, it directly optimizes the model to increase the likelihood or odds ratio of generating the preferred reasoning over the dispreferred one.
So it's directly pushing the model towards good security logic and away from the bad stuff.
Exactly. It helps instill this sort of inductive bias towards security-aware, structured reasoning directly into the smaller models.
So it's not just about the final answer, it's really baking in the process of sound security analysis.
That's the goal. And the paper makes a point that this is kind of the first time this detailed preference dataset approach with RLAIF has been applied specifically to software vulnerability detection across multiple languages.
Let's talk more about that dataset. Sounds like getting that right was absolutely crucial.
Oh, definitely. They put a lot of effort into it. They started by mining vulnerability fixing commits, VFCs, from the National Vulnerability Database for those 5 languages.
Okay.
And initially, they used a common heuristic. Assume the code before the fix was the vulnerable part. But they knew this can be noisy.
Noisy meaning the commit might fix the bug, but the prefix code snapshot isn't precisely the root cause or includes unrelated changes.
Exactly that. So to clean it up, they used GPT-4o for reannotation.
Wow, okay. How did that work?
They had GPT-4o score how likely it was that a specific function in the prefix code was actually responsible for the vulnerability. They set a high threshold, only kept functions with a score of 4 out of 4.
High confidence labels then.
Very high. And they didn't stop there. They had human security experts manually check a sample of these GPT-4o labels. And the agreement was really high, like 93% confirmed correct. They argued this makes their datasets labels more accurate than many existing SVD datasets.
That's a huge amount of work, but sounds worth it. And then they balanced it.
Yep, they merged these validated vulnerable functions with a set of known non-vulnerable functions to create a balanced dataset for training.
But they also tested on imbalanced data, right?
They did. For C# and Java, they created specific test sets with different ratios of non-vulnerable to vulnerable code going up to 10:1 to simulate real-world conditions better.
Smart.
And one more thing for generalization testing, they used a completely separate, externally curated Java dataset from another study, totally out of distribution data.
Okay, comprehensive setup. Let's get to the main results. RQ1. How does R2VUL stack up against other methods?
The results were pretty clear-cut. R2VUL consistently came out on top compared to a whole suite of baselines.
Like what?
Established SAS tools, SemGrep, SonarQuib, Fortified, TeamScale, then various flavors of chain of thought prompting, also standard classification fine-tuning, including CodeBERT, and models fine-tuned with standard instructions, both monolingual and multilingual ones.
So basically everything.
Pretty much, yeah, across all 5 languages.
And were the performance gains substantial?
Yes, quite significant.
Oh.
They showed, for example, the 1.5 billion R2VUL model on Python getting like a 12% boost in precision and over 9% in F1 score compared to just standard multilingual fine-tuning on a similar size model.
Wow.
And interestingly, those chain of thought methods, they were consistently the worst performers, even on the big 32 billion parameter teacher model.
So that really drives home the point that you can't just rely on the base LLM's reasoning for this task. Fine-tuning is key.
Absolutely. And the type of fine-tuning clearly matters. R2VUL's approach was demonstrably better than standard fine-tuning or classification. They even show that their 1.5B R2VUL model performed comparably to a 7B parameter model trained with standard multilingual fine-tuning.
So more efficient and more effective. What about comparing R2VUL to other AI models specifically built for reasoning-based vulnerability detection, like MSIVD or VUL-LM?
Right, they looked at those too. Both use code LLM 13b and mainly focus on C, C++. R2VUL outperformed them by a large margin.
Even on C?
Even on C and across all the other languages too. Their 1.5b R2VUL model on C achieved an F1 score that was like 58% better than VUL-LM and 17.5% better than MSIVD, according to
That's a massive improvement. Really shows the benefit of the structured reasoning distillation.
It really does seem to.
Okay, so that covers the baseline comparisons. What about RQ2, generalization? How did it handle class imbalance and totally new vulnerabilities?
That was another strong point for R2VUL on those imbalanced C# and Java datasets where safe code dominated. R2VUL, specifically the 1.5b model again, maintained the highest F1 scores even at the highest imbalance ratio, 10.1. It handled the imbalance better than both the classification model and the standard fine-tuned model.
Suggesting it's less likely to just ignore the rare vulnerable cases.
Seems that way, yeah. More robust in that sense. And then there was the test with out-of-distribution CVEs vulnerabilities the models hadn't encountered in training.
What happened there?
Kind of surprisingly, all the methods actually did a bit better on the unseen CVEs. The recall was higher.
Huh. Weird. Where would that be?
The paper doesn't speculate too much, but maybe the training set CVEs were harder. Or maybe the owed ones shared underlying patterns the models picked up on. Hard to say for sure.
Okay, but how did R2VUL compare specifically?
R2VUL still had the highest recall overall, but crucially, it had the smallest gap between its performance on seen ID and unseen owed CVEs. Just under 1% difference. Compared to like almost 12% for the standard SFT model and nearly 7% for the classification model.
Ah, okay. So R2VUL's performance was more stable between known and unknown vulnerability types.
Exactly. Less drop off, or in this case, less of a jump up. It suggests it's learning more general security principles.
And the final generalization test, that external Java dataset.
Another win for R2VUL, the 1.5b model got the best F1 score and really high recall on that completely unseen, manually labeled data. Strong evidence for its transferability.
Great. They also looked at hyperparameters, right? RQ3. How sensitive is this ORPO training?
Yeah, they mainly looked at the lambda parameter in ORPO, which balances the standard learning loss and the preference loss and also the number of training epochs.
What did they find?
They found lambda definitely matters. The value recommended in the original ORPO paper wasn't actually optimal for this task. They got the best results with a slightly higher lambda, around 0.6.
Interesting.
And they also saw signs of overfitting after about 3 or 4 epochs of training. The validation loss started to creep up, even though the reward accuracy kept climbing.
So careful tuning is definitely needed. Can't just set it and forget it.
Nope. Standard practice for deep learning, really, but good that they investigated it for this specific setup.
Okay, beyond the metrics, they also assessed the quality of the reasoning itself, didn't they?
Yes, a qualitative assessment. Very important. They took 100 samples and had LLMs GPNO 4.0 and Claude 3.5 Sonnet, plus human experts evaluate and compare the reasoning generated by R2VUL, one of the COT methods, COT reflection, and MSIVD.
How did they judge the reasoning?
They looked at things like completeness, did it cover all the key aspects, clarity, was it easy to understand, and actionability, was the explanation actually helpful for fixing or understanding the risk.
And the verdict?
R2VUL came out way ahead. Both the LLM judges and the human annotators scored R2VUL significantly higher on all those aspects.
Overwhelmingly preferred.
Pretty much. The LLMs preferred R2VUL something like 94% of the time in head-to-head comparisons, and humans around 92-93%.
That's compelling. Any examples?
Yeah, they included one in the paper, Java path traversal vulnerability. R2VUL nailed it. Identified the flaw, explained the path manipulation clearly, mentioned the CWE. The NSIVD gave some irrelevant details, and the Kata method kind of missed the main point.
So the structured reasoning really translates into more useful output.
It certainly seems to.
The researchers also acknowledged potential limitations, threats to validity.
Yes, they did, which is good scientific practice. They mentioned their use of Quen models, the NVD as the data source, but pointed to the external test set results as mitigation. Also discussed the hyperparameter tuning and the possibility that their specific structured reasoning template might not be the absolute best one possible.
Fair enough. And they situated this within the broader field. Related work.
Yeah, a solid review. They covered other LLM approaches for SVD, the COT limitations we discussed, other instruction tuning work like MSIVD, VUL-LM, LLM VUL-X, highlighting how R2VUL differs with its structured reasoning via RLAIF across more languages.
And compare datasets too.
Right. They discussed existing SVD data sets like Big VUL, Diverse VUL, etc., noting issues like label noise or lack of metadata, and positioned their new preference dataset with structured reasoning as a key contribution.
Okay, so wrapping up, what's the big picture takeaway here?
I think R2VUL marks a really significant advance. By shifting the focus from just getting a label right to improving the quality and structure of the reasoning process, they've shown a powerful way to leverage AI for security.
And using RLAIF to distill that into smaller models is key.
Absolutely. The fact that these smaller R2VUL trained models can match or beat bigger models and tools, that has huge practical potential for making effective vulnerability detection more accessible and resource-friendly.
The dataset itself also seems like a major contribution.
Definitely. That large-scale, multilingual preference dataset with structured reasoning could really fuel more research in this area. It's a valuable resource.
And the strong generalization results handling imbalance, unseen vulnerabilities, external datasets that really boosts confidence in its real-world applicability.
Right. It suggests the approach is learning something more fundamental about security flaws, not just surface patterns.
The hyperparameter findings are a good reminder about the nuances of training these models too.
And the qualitative results, showing why it works, the clearer, more complete, more actionable reasoning that really ties it all together.
So lots of exciting directions for future work building on this, I imagine.
For sure. Exploring different reasoning structures, maybe even more advanced RL techniques. There's plenty more to do.
Well, this has been fascinating. If you listening want to explore R2VUL further, definitely check out the paper and their dataset. We'll put the link in the description.
Yeah, Devin.
Let us know what you think. What parts of R2VUL seem most promising to you? Any questions pop up, drop them in the comments below. Thanks for joining us on AI Paper Podcasts for this look at R2VUL.